To set the stage, I thought I'd begin by actually saying a few words about the conventional Big Bang theory as it stood before inflation appeared on the scene. The underlying principle of this conventional Big Bang theory is that the universe as we know it began some finite time ago, and now we think that time is 13.82 plus or minus 0.05 billion years ago. The initial state was a hot, dense, uniform soup of particles that filled space uniformly. There's a popular cartoon image of an egg that's sitting in the middle of an empty space and suddenly explodes. That really never was the scientific picture of the Big Bang. The point is that we see the universe being completely homogeneous, and inflation, which I'll talk about in a few minutes, helps to explain that. But in the context of the conventional Big Bang theory, which is what I'm setting the stage up for now, this homogeneity had to simply be put in the initial conditions. So it was assumed from the beginning that all the matter filled space completely and was in fact already expanding. So the question you might ask is what existed before that? And the answer is who knows? We really have no idea what came before the Big Bang. There are some speculative theories that people have put together, but they're quite speculative. There's no general agreement on what happened before the Big Bang. I might add here that the conventional Big Bang is often described as the statement that space and time came into existence at the instant of the Big Bang. That's a possibility, but it's certainly nothing that you should bet on, because we really have no way of knowing. And in fact, in the picture of eternal inflation, which you'll be hearing about later, our Big Bang was actually just one event in a larger picture and was not really the beginning of anything in the absolute sense. So the picture is that within about 10 to the minus 35 seconds or so of when our region began to evolve, which would happen whether we have eternal inflation or appearance out of nothing, inflation began. So what is inflation? Inflation is a theory which is sometimes I describe as the bang of the Big Bang. That is, the conventional Big Bang theory really started with the universe already expanding. In spite of the fact that it's called the Big Bang theory, it really says nothing about the bang itself in the sense of what caused the tremendous period of expansion that we're still seeing the remnant of. That is, the conventional Big Bang theory is really only the theory of the aftermath of a bang. But inflation actually is a possible answer to the question of what propelled the gigantic expansion of the Big Bang. And before inflation, the expansion was, as I said, just assumed. So inflation explains this expansion in terms of gravitational repulsion, a repulsive form of gravity, which is somewhat novel to physics. In Newtonian physics, gravity is always attractive. But in the context of general relativity, gravity can become repulsive. The idea of repulsive gravity to me is so novel, in the overall span of my life at least, that I consider it kind of a miracle of physics, where I'll define a miracle of physics as anything that I would not have believed to have been true when I got my PhD. And one of those is repulsive gravity. Even though it was part of the theory of general relativity, it was not widely talked about. The theory of inflation from this method of counting miracles depends actually on two miracles. And the first of those is this miracle of gravitational repulsion. And the point is that since the advent of general relativity, physicists have known that gravity can act repulsively. And in fact, Einstein did use this option very early on in 1917 when he built his own model of cosmology. As you may know, he introduced this concept of a cosmological constant, which is basically a method of invoking this repulsive form of gravity, because he was trying to build a static model of the universe. And he wanted a mechanism that would oppose the normal force of gravity so that he could prevent the universe from collapsing under the force of normal gravity. So general relativity allows for this repulsive gravity, and in fact, modern particle physics suggests that at very high energies, there should exist states of matter that do the same thing as the cosmological constant does, causing this repulsive form of gravity to come into effect. So according to general relativity, a gravitational field can be created by pressures as well as energy densities. And that's really the key to allowing the possibility of repulsive gravity. And it's really dictated by the relativistic invariance of the theory. The point is that what looks like a pressure in one reference frame would contribute to the energy density to a moving observer. And that means that in a theory that's going to work for all observers, moving or not, they have to both be part of the source of gravity. So the way pressures work is pretty much what you would probably guess. Positive pressures, which are sort of normal pressures, lead to normal gravity, which means attractive gravity. But then you might infer that if there could be such a thing as negative pressures, a negative pressure really is a kind of a suction, a negative pressure would produce a repulsive gravitational field. The equation that actually describes the acceleration of the expansion of the universe is the equation shown here. A is the scale factor. The scale factor describes the overall proportion of the universe. Whenever the scale factor doubles, it means that all distances in the universe have doubled. And the acceleration of the scale factor is given by this formula, which is usually dominated by the first term, the mass density. And that makes the acceleration negative, which corresponds to attraction, slowing down the expansion. The pressure term appears here as a relativistic correction. Notice the 1 over c squared in the denominator, which is the hallmark of a relativistic correction. It would be 0 if c were infinite. But if the pressure is negative, that would allow this expression in parentheses to change sign, causing the acceleration of the universe to be positive instead of negative, a gravitational repulsion. And in fact, if the energy density is dominated by the potential energy of a scalar field, which can happen in states that we expect from particle physics, you find out that exactly the pressure is equal to minus the mass density times c squared, which means that the second term is 3 times as big as the first term, but with the opposite sign. So it overcomes it, producing gravitational repulsion. So let me go over the sequence of events now that constitutes inflation. The previous slide was supposed to explain essentially the underlying physics. But inflation proposes that a patch of repulsive gravity material existed in the early universe. And if inflation took place at the grand unified theory scale, as there's now some evidence for coming from the discovery of gravity waves, which I'll be talking about later, then this patch, the grand unified theory scale gives us the numbers, this patch would really only need to be about 10 to the minus 28 centimeters across to be large enough to ultimately become our entire observed universe. This, by the way, is more than 1 billion times smaller than the size of a single proton. So we're really talking about an amazingly small size for the piece of space that's going to ultimately become the entire observed universe. Now, since any such patch is enlarged fantastically by inflation, the initial density of such patches, or the probability of such patch forming in any given location, can be very low, and it doesn't really matter. As long as it eventually happens, it then becomes the entire universe, and possibly even much more. So the assumption is then that the gravitational repulsion was the driving force behind the Big Bang, and this gravitational repulsion causes this tiny patch to start to grow exponentially with a time constant of about 10 to the minus 38 seconds. So every 10 to the minus 38 seconds, this little patch would have increased in size by a factor of e, the base of the natural logarithms. So what we need is for this initial patch to expand exponentially by a factor of about 10 to the 28, which involves about 100 doubling times, 60 time constants, or 60 or 70. But it could have expanded much more. There's nothing that needs to be fine-tuned about the amount of expansion. There's a minimal amount needed to explain what we see, but there could be vastly more expansion, which would just mean that the region that we're living in is vastly larger than what we have been able to see. In any case, at the end of inflation, the size of the region that will ultimately become our observed universe would have been about the size of a marble, about a centimeter or so across. And then at the end of inflation, the acceleration turns off, but this little marble-sized region is still expanding, and it continues to expand and coast, starts to slow under the ordinary force of gravity at that point, but continues coasting right up until the present day. Now, what ends inflation is that the repulsive gravity material is unstable, so it decayed pretty much like a radioactive substance decays. That is, the decays are just random. There's no way of predicting where or when a decay will take place. But when the decay does happen, the energy that has been locked up in this repulsive gravity state gets released and becomes a hot soup of ordinary particles, which is exactly the starting point of the conventional Big Bang theory. So inflation plays the role of being the prequel to the conventional Big Bang description. Now, there's a very important feature here which needs to be explained and leads to the second miracle that I want to talk about, which is that during the exponential expansion, if we were talking about ordinary matter inside this region, it would thin out by a fantastic factor because it's expanding by a factor of 10 to the 28 linearly. That means 10 to the 76th in volume. So the density would fall by that incredible factor if we had ordinary substance inside. But it turns out that this repulsive gravity material actually does not thin out at all during the exponential expansion, which seems like it's going to violate conservation of energy because we have a fixed energy density and the volume is expanding by a colossal factor. So how can that be consistent with energy conservation? Obviously, this is a place where we need another miracle, and it's coming up. The miracle is not any violation of energy conservation. Energy is rigorously conserved as far as we know in all cases, and this inflation theory would not fly if it violated energy conservation. But what protects it is the peculiar feature that the energy of a gravitational field is actually negative. Now, this is a fact that's true even in Newtonian gravity, and it's also true in general relativity. For some reason, though, it's never become a well-known fact about physics, except maybe recently, which is why it classifies as a miracle. It's certainly nothing that anybody taught me through the time I got my PhD. And the way it works then is that the negative energy of the gravitational field that fills this region as it exponentially expands cancels the positive energy stored in the matter, so that the total energy can remain constant and possibly exactly equal to zero. So the bookkeeping is shown here. The total energy is the matter plus radiation, which is in black, positive. The gravitational energy is negative, so it's shown in red as in a financial ledger. And it all adds up to about zero. And that means that this expansion could go on literally forever without any problems concerning energy conservation. I thought I'd say a few words here about why it is that we know that the energy density of a gravitational field is negative. So this is kind of a thought experiment which is intended to illustrate that fact, all in the context of Newtonian gravity. You just have to take my word for it that similar things happen in general relativity. So we want to imagine a thought experiment of having a spherical shell of matter, empty inside, just a shell on the surface. And I need to know what the gravitational field of that looks like. And it was calculated by Newton. It's in his Principia. So I'll just tell you the result. Many of you, I'm sure, know this. And if you don't, you'll just have to believe me. The result is that outside the shell, the gravitational field is exactly what it would be if the whole mass of the shell were just a point mass at the origin, just a 1 over r squared force. So these force lines shown outside are supposed to represent that. Inside the spherical shell, the gravitational field is exactly zero. It cancels out in the different directions. So the sum, when you add up the force due to the attraction to each bit of mass around the shell, adds up to exactly zero. And Newton figured that out too. So now what I want to do in my thought experiment is to imagine that this shell is made out of something flexible, putty of some sort, clay, so that I can allow it to collapse under its own self-gravitational force. There'll be a force on the shell pulling inward. Every particle in the shell will be pulled by the other particles of the shell, and the net force will be inward on any particle of the shell. So I want to take advantage of this inward force to generate power So in my thought experiment, I'm going to imagine attaching a whole large set of generators by strings. The generators are in fixed position. The strings go from the generators to the surface, and I'm going to allow the surface to collapse under the force of gravity, pulling on those strings, turning the generators, generating power. So in this second stage here, power is generated by the inward motion of the shell. Then we stop and ask ourselves what's happened all in all. How do we add things up? And in this final picture, what's being shown is the position of the outer shell, which is shown as this dashed line, the new position of the shell when we finish the process, shown as the solid black line, and the gravitational field. And this shaded region is the region which has gravitational field at the end of the process, but had no gravitational field at all in the first picture at the beginning. So the net effect of the entire operation is to generate power by the generators that we pulled on the strings and activated, and to create a new region of gravitational field where previously there was no gravitational field. So the only way that could be consistent with energy conservation is if somehow the energy for the power that was generated can be accounted for by this new region of gravitational field. And that means that the new region of gravitational field has to correspond to a negative energy. So the total energy is the same as what we started with. So this is a simple demonstration in the context of Newtonian gravity that the energy of a gravitational field has to be negative. So I want to actually talk about 4 separate pieces of evidence for inflation, the first of which is the large-scale uniformity of the universe. The cosmic background radiation is our strongest evidence for this uniformity, and astronomers have now made very careful measurements of the uniformity of the cosmic background radiation, and have found that it's uniform to 1 part in 100,000, which I think is really amazing. One way of perhaps getting some handle on how uniform by 1 part in 100,000, what it actually means, is to imagine, for example, trying to construct a marble that's round to an accuracy of 1 part in 100,000. And you can calculate how precisely the surface of the marble has to be constrained, and it turns out to be something on the order of a wavelength of light. So modern technology knows how to do that. We build lenses that are accurate to a fraction of the wavelength of light. But it would really mean that the marble would have to be round to the accuracy of a high-quality lens in order to be this round. But the universe would just fine this way. We don't have to do any special grinding. And somehow the universe got to be this incredibly uniform state without our knowing how it happened. So the other important point in trying to understand what this means is to know something about the history of the cosmic background radiation. It says here that the cosmic background radiation was released when the universe was about 380,000 years old. By released, what's meant is that prior to this time, the universe was so hot that everything was a plasma. And in a plasma, photons are constantly being scattered off of the free electrons in the plasma. So even though each photon is instantaneously moving at the speed of light, as photons do, the photons are constantly being rescattered into different directions. And the net result is that during the early period, before 380,000 years, the photons essentially went nowhere. They were just basically glued to the hot matter, to the plasma. Then at 380,000 years, the universe cooled enough so that the matter neutralized, and suddenly we had a neutral gas like the air in this room. And neutral gases are highly transparent to photons. And it's a little dangerous to just imagine directly extrapolating from the room to the universe. But in this case, it works. You can go through the mathematics. The universe really is transparent to photons since the time of recombination, since the time when the universe became neutral. So the result of that is that the photons that we see today in the cosmic background radiation really have been traveling on straight lines since 380,000 years after the Big Bang. And the implication of that is that it gives us an image of what the universe looked like at 380,000 years, just as the photons traveling from my face to your eyes let you know what my face looks like. It's as simple as that. So what this means is that the universe itself was incredibly uniform to 1 part in 100,000 accuracy by 380,000 years after the Big Bang. So that now gives us a well-defined challenge. Can we explain how the universe got to be so uniform by this time? Now I should add that you could always just assume that the universe started out completely uniform. We don't really have a theory of how the universe actually started out. So if you want to make that assumption, that's fine. But it seems to be a very bold assumption. If, on the other hand, you'd like to be able to describe how the universe became uniform through physical processes that we understand, then we're forced to address this question. And that's the context in which inflation gives a very nice answer. In the context of conventional cosmology, without inflation, you can do a pretty simple calculation to trace these photons back to where they came from. So you can imagine looking at a photon coming from that direction in the sky and another photon coming from that direction in the sky and trace them back. And what you find is that when those photons were emitted, they were separated from each other by about 100 times the distance that light could have traveled up until that time. So that indicates that if you believe that nothing travels faster than light, and as far as we know that's true, there's no way that that photon could have known anything about what was happening to that photon at the time when these photons were emitted. Yet somehow that photon and that photon knew how to be at the same temperature at the same time to an accuracy of 1 part in 100,000. So that's the issue, sometimes called the horizon problem. And within the context of the conventional Big Bang theory, there's no way to solve that. However, inflation provides a very nice solution. In inflationary models, we're inserting into the scenario of the universe this period of incredibly rapid exponential expansion. And that means that if we imagine taking the visible universe today and tracing it backwards in time, when we come to the period of inflation, it suddenly becomes rapidly much, 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 much smaller because we're doing the inverse of the expansion. So before the inflation started, the region was vastly smaller than anybody would have thought in the context of conventional cosmology. So before the inflation, there is plenty of time for this tiny region to become uniform in both density and temperature in the same way that the air in this room spreads itself out to an approximately uniform temperature and approximately uniform density. That's basically what thermal equilibrium is about. And then, once this uniformity is established on this tiny scale, inflation takes over and magnifies this tiny speck to become big enough to include everything that we see today, giving us a very simple explanation for why everything that we see today, including the cosmic background radiation, is incredibly uniform. Okay, the second issue I want to talk about is what's called the flatness problem. Why was the early universe so flat? Should say a few words about what's meant by flat. First of all, flat does not mean two-dimensional, as I discovered sometimes my audiences think. Flat can mean that, of course, but it's not the meaning I have in mind. Here, by flat, I mean Euclidean, obeying the axioms of Euclidean geometry. According to general relativity, the universe doesn't have to be Euclidean. If you assume that the universe is completely uniform, then you're limited to 3 possible geometries for the universe. Of course, if you don't assume it's uniform, it can be lumpy in all kinds of complicated ways. But the universe certainly appears to be uniform, and now inflation gives us an explanation of that. So if we assume uniformity, just to understand what the options are, there are basically 3 kinds of geometries. There's a closed geometry, which is similar to the surface of a sphere and has the property, like the surface of a sphere, that if you draw a triangle, instead of the 3 angles adding up to 180 degrees, as Euclid tells us they have to, on the surface of a sphere, they add up to something a little bigger than 180 degrees, as I think you can see from the illustration. That's an accurate perspective, by the way. I drew that thing myself. Conversely, One can talk about an open geometry, which is kind of like the surface of a saddle, it's often described as. And in an open geometry, again, as I think you can see from the picture here, the edges, the corners of the triangle get pinched by the curvature, and the sum of the three angles adds up to a little less than 180 degrees. And right on the borderline between those two possibilities is a flat geometry, the geometry of Euclid, where the three angles add up to exactly 180 degrees all the time with no other option. So that's the meaning of the concept of flatness. And the point is that our universe today and the early universe were rather extraordinarily flat. Well, see, first of all, I said that the general relativity links the flatness to the mass density of the universe, or maybe more precisely to a relationship between the mass density and the expansion rate. There's something called the critical mass density, which is a number that depends on the expansion rate. It's not a universal constant. And this critical mass density is the density that would make the universe exactly flat. And cosmologists tend to talk about the actual mass density in terms of this ratio called omega. Omega is just the ratio of the actual mass density, whatever it's found to be, divided by this critical mass density, a number that you calculate that depends on the expansion rate. And if omega is 1, the geometry is exactly flat. If omega is bigger than 1, the geometry is closed. And if omega is less than 1, the geometry is open. Now, the fact of physics that gives rise to this flatness problem is that it turns out that the universe is near omega equals 1. And furthermore, omega equals 1 is an unstable equilibrium point. And by unstable equilibrium point, what we mean is that if omega is ever exactly equal to 1, it will stay exactly equal to 1 forever. But if omega is just a little bit off from 1, it will rapidly start to fall in that direction, just like a pencil balancing on its tip. If the pencil is exactly straight up, it will stay straight up forever, at least according to classical physics. We'll pretend quantum theory doesn't apply to this pencil, even if it applies to other pencils. But if this classical pencil is leaning just the tiniest bit in either direction, it will then start to fall in that direction and will fall pretty rapidly once it gets going. So omega equals 1 is just like that. If omega is exactly equal to 1, it will stay 1. But if omega in the early universe were just a tiny bit bigger than 1, it would rapidly start to rise towards infinity. And if omega in the early universe were just a tiny bit less than 1, it would rapidly trail off to 0. And to make that quantitative, we need to consider some particular time, because it depends on what time you're talking about. So let's talk about the universe at 1 second after the Big Bang. I should maybe mention that 1 second is not a crazy time to talk about in terms of conventional cosmology even. One of the big successes, I didn't have a chance to talk about all the features of conventional cosmology, but one of the big successes of conventional cosmology is the accounting it gives for Big Bang nucleosynthesis, how the elements were formed in the Big Bang. And those processes began at about 1 second after the Big Bang. And there's very good agreement between the observed abundances of the light chemical elements in the universe and what you calculate from the Big Bang model. So the Big Bang model is really rather directly tested by nucleosynthesis at timescales as early as about 1 second. So 1 second is a fairly natural time to talk about here. So if we think about the universe at 1 second after the Big Bang, what we find if we put in the detailed calculations connected with this instability is that at 1 second after the Big Bang, the value of omega must have been just what it needs to be, which is 1, to an accuracy of about 15 decimal places. Or else we would not be consistent with what we see today. I should add that in conventional cosmology, that's something of a mystery, because there's nothing in conventional cosmology that determines the initial value of omega. It's just something you have to put in by hand. So like the previous problem, you can solve it by fiat if you're willing to just assume that the universe started out with omega exactly equal to 1. But if you don't want to assume that and want to try to have some dynamical understanding of how omega got to be so close to 1, then you really cannot do it within the context of conventional cosmology, but inflation offers an answer. So the inflationary solution comes about because inflation changes the whole description of the expansion of the universe. Instead of the expansion slowing down, the expansion is speeded up by inflation, so signs of equations in key places are changed. And in fact, inflation drives omega to 1, and it drives omega to 1 incredibly rapidly. It drives omega to 1 exponentially. So that means that in the context of inflation, omega could start off being almost anything. It could start off being a tenth, it could start off being 10, it could start off being a hundredth or 100. The further away you start from 1, the more inflation you need to smooth things out. But if you have the amount of inflation that we talked about 100 doublings, that will take you from any reasonable value of omega to a number close enough to 1 to be consistent with what we see. And if you start further, you just need a little bit more inflation. So no matter where you start, inflation will solve the problem as long as you have enough inflation. Now, in fact, because inflation drives omega to 1 exponentially, it means that if you overshoot a little bit, you get a lot closer to 1 than you thought you needed to be. So in other words, the mechanism essentially always overshoots and produces a universe that's not merely as flat as what we observe, but rather a universe that's much flatter, much closer to omega equals 1. So that really gives rise to a prediction of inflation. The prediction is that today, when we measure omega, we should get a number that's, to the accuracy that we can measure it, equal to 1 exactly. So that prediction had some interesting history. Until about 1998, astronomers were not finding omega equals 1. Rather, they were finding omega equals 0.2 or 0.3. Now, I have to admit, thinking back, this always made things a little bit uncomfortable for me when I had dinner with astronomers. They would enjoy pointing out to me that although inflation is a beautiful theory, it doesn't seem to correspond to reality because it predicts omega should be 1, and we can see obviously that it's not. However, the story ends more happily than that. The latest observation of omega, which comes from the Planck Satellite combined with some other data, is that omega is equal to 1.0010 plus or minus 0.0065. Or to simplify that statement, omega is equal to 1 to an accuracy of about 0.5%, the accuracy that we know it. So everything is now completely consistent with omega equals 1, which is gorgeous. Now I enjoy having dinner with astronomers. And the new ingredient is what's called dark energy, which probably you've heard about in other contexts. The point is that 1998 marks the year in which astronomers discovered that the expansion of the universe today is not slowing down under the influence of ordinary gravity, but rather today the universe is actually accelerating. And that means that today the universe is apparently, if general relativity is the right theory, filled with some material with a negative pressure, just like the negative pressure that we talked about driving inflation in the early universe. So it's again repulsive gravity, it's again negative pressure. It's probably not in any way the same substance. There's no reason why it should be, although there are some theories that do relate them. So apparently for the last 5 billion years or so, the universe has been dominated by this dark energy and has therefore been accelerating. And the beauty for the present discussion is that when you add in the energy of the dark energy to everything else that we know, you bring the total up from about 0.2 or 0.3 up to 1, to a very high degree of accuracy, about 0.5%. Besides the very extreme uniformity that we see on large scales, on smaller scales, we of course see a lot of structure to the universe. There are clusters of galaxies, there are stars. All of that structure had to come about somehow. And we believe it came about because the early universe, although incredibly uniform, was not exactly uniform. Apparently the early universe, and we really see this now directly in the cosmic background radiation, when we look at this picture at higher resolution, the early universe had an almost uniform mass density, but there were tiny ripples superimposed on that almost uniformity. And it's those ripples that gave rise to all of the structure that we see in the universe today. And the reason why a small ripple can produce a very highly clustered galaxy or a cluster of galaxies is because of the fact that the entire system that we're describing here is gravitationally unstable. And what I mean by that is that if you start with a region with just a tiny excess of mass density, 1 part in 100,000 higher than average, that region will produce a very slightly stronger gravitational field pulling matter into the region. More matter will then be pulled into the region. The density will become more than 1 part in 100,000 higher than average, and that will create a still stronger extra gravitational field pulling matter in. That will pull more matter in, and the system is unstable and ultimately forms real clusters of mass, which are the galaxies, the clusters of galaxies, and the stars. So we expect to see non-uniformities in the mass density of the early universe, and we expect that to show up in the cosmic background radiation. But the question still is, where do these ripples come from? And again, in conventional cosmology, there was really no explanation whatever. People were already aware that these ripples had to be there, although they had not been seen. But before inflation, people were aware that these ripples had to be there, and people just imagined putting them in by hand. Nobody had any idea where they could possibly come from. But in the context of inflation, we actually have an answer to that question, and the answer is, in some ways, mind-boggling. The answer that we're proposing here is that the ripples on the universe, which ultimately becomes the entire structure of galaxies and clusters that we see today, actually originate as quantum fluctuations. The point is that quantum theory, unlike classical theory, is fundamentally probabilistic. There's no way of making definite predictions, really, of anything in a quantum theory. So when the classical theory is predicting an almost uniform mass density, the quantum theory is going to tell us it can't be that uniform. There's just too much uncertainty. So in some places, the mass density is going to be a little bit higher than the classical prediction, and in other places, it's going to be a little bit lower than the classical prediction. And that, at least qualitatively, sounds exactly like the ripples that I talked about that we must need. And we can do this quantitatively. We can put in quantum corrections to our classical description of inflation and calculate what these quantum fluctuations should do. When we do that, we find that we do not know enough about the details of inflation to predict the amplitude of these ripples. We cannot predict how intense they are. But what we can predict is the spectrum of the ripples. And by spectrum, what I mean is that these ripples, like sound waves, can be broken up into ripples of definite wavelength. And then you can talk about how the intensity of the ripples varies with the wavelength. And that's exactly what you would mean if you talked about the spectrum of a sound wave. It's really the same thing here. Here it's best to talk about wavelengths and not frequencies. Often when you talk about sound waves, you talk about frequencies. These waves don't oscillate the same way that a sound wave does, so frequencies are not so well defined. But if you think about it in terms of wavelengths, it's exactly the same as what you would think of as a spectrum of sound waves. Now what we actually see are these ripples on the sky rather than ripples in three-dimensional space, so you have to do a further calculation to ask what should these ripples look like as projected into the cosmic background radiation that we see, and you can then predict how the spectrum should look, and now it can be measured with rather extraordinary accuracy. They were first measured by the COBE satellite in 1992, later more accurately by the WMAP satellite, along with a large number of ground-based measurements and balloon measurements as well. And now the most precise picture we have of the cosmic background radiation comes from the Planck satellite. And the results are beautiful. There's the result from the Planck satellite. What's being shown here, on the horizontal axis, we have the angular wavelength, shown as angules on the top, going from long wavelengths on the left to very short wavelengths on the right. So this is the angle of the wavelength that you'd see of this pattern on the sky. On the bottom axis, they show things called multiple moments. And if you know what that is, great. And if not, we don't have time to talk about that now. But it really is just another way of characterizing this angular wavelength. So all of the physics really can be seen on the top version of the horizontal axis. On the vertical axis, we have the intensity of the ripples. And what is shown here are red dots with error bars attached to them. That's the measurement. And what's also shown is this green line, which is the theoretical curve coming out of inflation. Now, I should be honest and admit that there are 6 parameters that are being fit in constructing that theoretical curve, because they're just things we need to know about the universe that we don't know how to find out any accurately enough to do this, except by taking it from the cosmic background radiation itself. The most important parameter that's fit is the overall height. The overall height, as I mentioned, we don't know enough about inflation to predict it. In principle, it would be predicted if we fully understood the mechanism of inflation. But the height is put in by hand, and a few other parameters, like the amount of dark energy, is put in by hand here. But nonetheless, it's a rather extraordinary fit. Might mention something about this green band that we have on the left. That green band is what goes by the name of cosmic variance. It corresponds, it's only significant for the longest wavelengths. Short wavelengths, it's in principle there, but too small to see. What it corresponds to is the fact that what we're doing is looking at the results of a quantum experiment, an experiment which is fundamentally probabilistic to begin with. And that means that we can't predict exactly what we should see. We can only predict what we should see on average. For the short wavelengths, we get to see many, many waves of short wavelengths on the sky. So we're talking about an average of a large number of random numbers, which then gives a very definite value. For the very long wavelengths, we can only see a few waves of those wavelengths. And that means there's significant uncertainty in the prediction, because the prediction is probabilistic. We can only predict what the average should be and what the distribution should be. We can't predict what number will actually be seen in our universe. In principle, if we could go to other places in the universe and measure this curve from many different galaxies, we'd be able to get around this problem of cosmic variance. But because we can only see one universe from one location, there's just uncertainty in the prediction, which is the inherent uncertainty of any quantum mechanical prediction. The fourth item I want to talk about is gravitational waves, which have now been seen by BICEP-2 just a few months ago. The announcement was made on March 17th of this year. So along with density perturbations, inflation also predicts gravitational waves. And again, it's a quantum phenomena. The point is that quantum effects on very short length scales will mean that the geometry of space itself will be constantly fluctuating. And normally, this is confined to incredibly short length scales and totally invisible to us, but part of our theory of quantization of gravity. What inflation does is it stretches these quantum fluctuations to very large scales, which is essentially the same thing that happens with the density perturbations that I talked about earlier. And therefore, these fluctuations now become macroscopic enough to actually have measurable consequences. So the gravitational waves these gravitational waves are produced during inflation. Now, this cosmic background radiation that we look at was, as I said earlier, released at about 380,000 years after the Big Bang. But the gravitational waves created at the time of inflation can transfer their influence to the cosmic microwave background radiation by causing disturbances in the plasma that fills the universe at that time. And the result is that it imprints its patterns onto the cosmic microwave background. If you're only measuring the unpolarized radiation, that is, if your detectors are not polarization sensitive, you cannot really see directly the effects of the gravity waves. But it turns out that if you can measure the polarization of the cosmic background radiation, and then, of course, we're talking about measuring the fluctuations in the polarization of the cosmic microwave background radiation, then you can see specific signs which, as far as primordial sources are concerned, can only be created by gravity waves. And those are called the B modes. The other modes are E modes, where E and B refer to analogies between electric and magnetic fields. E modes can be produced by density perturbations, but only gravity waves can produce B modes. So these B modes were discovered in a very widely touted news conference on March 17th of this year. The discovery is spectacular, but I have to admit that since the original discovery, other groups of physicists have looked more carefully at the possibilities of contamination of the signal by foreground sources, that is, sources close to us, like for example, dust in our own galaxy. And right now it's somewhat uncertain whether these results are going to hold up or not. Okay, so these gravity waves, if they're real, have often been called the smoking gun of inflation, mainly because they're harder to produce from other kinds of theories that people might invent than the density perturbations, for example, are. So as far as we know now, at the present time at least, there are really no other theories that predict gravity waves other than inflation. Assuming that these gravity waves might be real, they are incredibly important to our understanding of physics as a whole and not just inflation. In particular, these gravity waves, or the gravity waves as seen in the cosmic background radiation, would really be the first time we've ever actually seen a gravity wave at all. Previously, we've seen clear evidence for energy loss due to what we think are gravity waves. In binary pulsar systems, we could see binary pulsars lose energy through gravitational radiation. And the amount of energy loss agrees very, very well with what you would calculate from general relativity as the expected energy loss due to gravitational radiation. So in that sense, the existence of gravitational radiation seems to be confirmed, but that's not a direct confirmation of what a gravity wave actually looks like, which we would be seeing for the first time in the cosmic microwave background radiation through these polarization measurements as done by the BICEP2 team. In addition, if these observations are corroborated, they would also be, in fact, the first direct experimental evidence that we have. I don't need the word direct there. It's really the first evidence that we have, first experimental evidence that we have that gravity is quantized at all. Now, this is not a big surprise to most theorists. We've always thought that gravity must be quantized because we don't really see any easy way that we can imagine to have classical gravity interacting with a quantum description of matter. So for the consistency of the whole picture, almost all physicists believe that gravity needs to be quantized. But this would be the first direct evidence, first evidence that we actually see experimentally that gravity is quantized. Next, another important feature of this observation, if it can be corroborated, is that it gives us our first handle on the energy scale at which inflation took place, or maybe more precisely at what the expansion rate of the universe was at the time of inflation. Believe it or not, we don't know that number, and there's a range of maybe even more than 10 orders of magnitude of what that number might be. The gravity waves pin that down because the intensity of the gravity waves that you see depends really only on the expansion, which is just pulling these gravity waves from microscopic scales to macroscopic scales. So the strength of what you see ends up really just depending entirely on the expansion rate. So seeing these B modes is really a direct measurement of the expansion rate of the universe at the time of inflation, which we don't know. If the measurement of the BICEP2 team holds up, then that tells us what the energy scale was for the universe. The energy density of the universe, V stands for potential energies, potential energy density. We always work in units where h bar and c are 1, so this factor doesn't do anything. But if you don't use units where h bar and c are 1, there has to be a factor of h bar c cubed here. This number to the 1/4 power is an actual energy, which we think of as being the energy scale of inflation. And with r equal to 0.2, r being the ratio of the power in gravitational perturbations to the power in density perturbations, just think of r as a measure of the intensity of the gravity waves. So r over 0.2 would be 1 if the measurement is exactly as originally stated. So this would say that the energy density of the universe at the time of inflation was characteristic of an energy scale of 2.2 times 10 to the 16th GeV, which happens to be exactly the energy scale of grand unified theories. So if it's right, it's a very interesting piece of evidence that grand unified theories might be correct and might be intimately connected to inflation. I have one more slide about implications of gravity waves. One of the nice implications from my own point of view is that if this result is corroborated, it rules out certain alternative ideas to inflation, and in particular the cyclic ekpyrotic model, which you may or may not have heard of. If you haven't, that's okay with me, but if you have, this would rule it out if it holds up. This paragraph mentions that the value obtained for R by the BICEP2 team was actually already in conflict with lower values of R that have been set as limits by other experiments, and in particular both Planck and WMAP, these two satellite experiments that measured the cosmic background radiation. Now, neither of those experiments measured the polarization. What I'm quoting now from both WMAP and Planck come only from measuring the radiation without looking at the polarization. But without looking at the polarization, you could ask yourself how much B-mode contribution could there be just given the total. The B-modes add to the total radiation that you expect to see. And based on that, these groups have set limits that R should be less than 0.11. They both came up with the same limit. And the measurement by the BICEP2 team of R equals 0.2 is larger than that. So that's one of the issues that needs to be resolved, and it's certainly part of the overall issue of how much of what the BICEP2 team saw really is primordial radiation and how much might be due to other sources of contamination. Now, if these observations are correct, it really is only the beginning of the excitement, because once one can see these B modes, evidence of gravitational waves, one has a whole new handle on astronomy to explore. That is, one wants to measure next how the intensity of these B modes depend on their wavelength to get a curve comparable to what I showed you for the density perturbations. And it's just as exciting as the first curve, and there's a fantastic amount of new information to be gleaned there. And what it would tell us is how the expansion rate of the universe varied during the inflationary process, which really pins down the details of the inflationary mechanism, which could be very, very interesting.